All right, hello everybody. And Eric, thank you for saying hi everybody. I hope you said that when you heard me. I wanted to just double check before we start that everybody can see my face, and more important than that is hear my voice. So if you want to just answer in the troll box. Okay, awesome. Yeah, we got some yeses. So hi everybody. I'm Joshy Orndorff. I work at Parity Technologies, and I'll tell you about what I do there and what Parity does shortly. Um, I think many of you have been to Crowdcast before, but probably several of you haven't. So feel free to, at any point, participate in the troll box where it says "say something nice." I'll check that occasionally. I'll also be sharing my screen, so I won't see what you say instantly, except right now. And then there's also an "ask a question" button, and feel free to use that. So as I'll say shortly, I really like questions, and the first part of this presentation is pretty structured, and I'll probably stick to the structure. But the second part is pretty flexible, and so I'd love to really dig into your questions. So if you were at part one, you might remember that, and we spent the last bit digging into questions, and we can do that again today also. So let me share my screen, and we'll get started. All right, cool. So I guess maybe could anybody just confirm again whether you see my screen? It might look like a sort of infinity of windows. Yep. Okay, cool. Great. That's good. So here's where we're going to start. Okay, and how about the slides? I'm not going to check like every time I change, but just at the beginning to make sure it's working. Okay, cool. I'm flipping back and forth to the slides. Great. Okay, that's awesome. So this is Substrate Part 2, Substrate Recipes. You might have been here for Part 1. That's awesome. And you might not have been here for Part 1, and that's totally fine too. I'm going to start with a quick recap of what we talked about before, just to sort of frame what we're going to talk about today, and then we'll move on into the recipes. So, and yeah, so for starters, that's me, Joshy Orndorff. That's my Alaska look. Now I'm not rocking that look anymore. A little bit about me. I was a physicist. That's what I went to school for. After grad school, I became a high school teacher, and I taught computer science and physics classes for several years. And eventually, I was thinking enough about blockchain that I decided I should make a career switch. So in 2018, I started working in the blockchain industry, and in 2019, I started working at Parity. And two of my big ongoing tasks or projects at Parity are the Substrate Recipes, which is what this is all about, and also Substrate Seminar, which I want to invite all of you to. The link will be at the end. Substrate Seminar is a weekly learning call, a lot like this, but not totally like this, because at Seminar, it's a Zoom call, and it's a little bit more interactive. So here I'll be explaining all about the recipes and maybe answering some questions. But at the seminar, it's more of an everybody's collaboratively learning together sort of situation. And so if you like today's session, or if you want to learn more about Substrate, or if you want to help us all learn about Substrate together, I'd invite you to come join us at the seminar. It's every Tuesday at 1400 UTC. And like I said, the link and everything will be at the end and in the follow-up email. So the last bullet point, I love Substrate. What can I say? Ever since I first heard about Bitcoin, I thought it was cool that anyone could launch a blockchain without permission. And that's sort of become more and more true as time has gone on. At the time, anyone could launch a Bitcoin-like chain by copying the code, or a chain of their own design by writing the code from the ground up. But in practice, it took a lot of engineering and preparation work, and Substrate aims to solve that. So let me not get ahead of myself and just point out this last bit. I love questions. Please ask questions. Like I said, the second part of this webinar is open to talk about whatever parts of the recipes or Substrate development in general you guys like. And so if you put questions into Crowdcast, we'll address them. So, all right, so I work at Parity. So what is Parity? Well, it's a development company who has built several blockchains. So Parity was first famous for their Ethereum client. It was for a long time known as Parity Ethereum, and now it's called Open Ethereum and is owned by the community. We also have a Bitcoin client, Parity Bitcoin. And as you probably know from the name of this Crowdcast, we're now building Polkadot. So, and actually those are sort of the big three, but there's other chains we've built in there too, including a Zcash client. And if you're a programmer, you know that abstraction and isolating patterns is a really useful and powerful tool, and that applies definitely in blockchain development as well. So by the time Parity had built this many blockchains, you can imagine thinking like, wow, all these blockchains have some things in common. They all have sort of like a networking layer. They all gossip messages in this P2P way. They all have this underlying concept of a blockchain data structure and verifying from Genesis and all that stuff. And so Substrate is actually the abstraction of that pattern of all those things that a blockchain, that the various blockchains have in common. So Substrate is an open source, modular, and extensible framework for building blockchains. So it's not a blockchain itself. It's a bunch of Rust code. It's a framework written in Rust that you can use in order to quickly build your blockchain, so that you only have to code the parts that are relevant to your particular application and not code every single piece, even the stuff that'll look the same as many other blockchains. And Substrate actually provides all the pieces you need to get started. When you get started with Substrate, a common way to do it is to just build an already written chain and start playing with it. And so we have like a node template for that, or several projects in the recipes that we'll see today that you can actually build and just start playing with. So when you do go to write your own chain, you just take whichever of those pieces you want. And in most cases, you can take almost everything from Substrate and just write very little of your own code. So like, here's just an example of what comes with it. You know, you're going to need a storage backend to store all of the blocks that you've been receiving and authoring on the network and all of the state of the blockchain. Obviously, you're going to need a P2P networking layer so that the nodes in your network can gossip transactions and blocks around and stay in sync. You need the transaction queue logic to queue up whatever, you know, balance transfers or whatever arbitrary transactions are coming into your blockchain. Consensus to agree on the state of the chain. And then you need a runtime. And although I wrote it here last, runtime is in some sense the most important part of the chain. It's your application's logic. So whatever the thing is that your chain does, that's the runtime. In Bitcoin, the runtime is a cryptocurrency. In Ethereum, the runtime is the Ethereum virtual machine, or EVM. In Polkadot, it's keeping track of the heads of all the parachains and reaching consensus over them, and some other stuff, like it has the dot token and on-chain governance, for example. And each one of these pieces that comes with Substrate, you can either use it as it is, or you can customize it or extend it. Or if you want, you can say, I don't want to use your consensus engine at all. I'm just going to write my own and fit it in with the rest of Substrate. So let me just pause a second to see if there's any questions or anything. Oh, let's see. If you want to make the slides bigger, you can click the, oh, okay. Like make focus screen. Oh, okay. Oh, interesting. So can you, this looks full screen to me. Is this full screen for you guys? Well, no, it's not. Oh no. Okay. 50-50. Oh, maybe if I turn off my video cam. Okay, maybe that will be better. So sorry for the small slides. Glad I looked back before we got into too much of the meat. Yeah, nice. Okay, cool. All right, so let's carry on. So, okay, here it is. This is the architecture of an individual substrate node. So it's not like a whole blockchain network. It's just an individual node. And there's a bunch of pieces in here. And the big gray circle is sort of like the boundaries of the node. And the pink things that are sticking out the side are ways that this node can communicate with the external world. So for example, we've got this libp2p connection here. And as you can tell from the name P2P, this is how the node communicates with other peers on the network, other nodes that look just like this one. And the JSON RPC is remote procedure call. This is how users of your chain, or their front ends, their agents, interact with the blockchain node. So this is, for example, where you submit transactions or where you read the state of the chain, like if you're checking your balance or checking if your crypto kitties have finished breeding yet, or checking if your smart contract call has executed to completion. So that's what the JSON RPC is. And then there's all these other pieces inside here that I talked about earlier, and I don't need to go into too much detail about now. And then there's this bit up here, the runtime, and that's the, like it says here, the application logic that makes this chain special. So whatever the application is that your blockchain is trying to be, or the problem it's trying to solve, that logic goes into the runtime. So most of the node is, well, all of the node is written in Rust and built into native code. So that means like compiled down to x86 assembly, or, you know, machine code that runs on your specific computer hardware. And then the runtime, in addition to being compiled to native, it's actually also compiled into WebAssembly, or WASM. And the WASM binary is stored on the blockchain. And that's what allows for Substrate to do some really cool stuff like on-chain governance and forkless runtime upgrades. So for example, if you find a bug in your runtime, or if you decide you want a new feature to your runtime, or you just want to change it, tweak some parameters somehow, with Substrate, you can do all of that without having a hard fork in your chain. And that happens because the runtime is compiled into WASM. And I think we got into that a little bit last time. I don't want to dive into it too deep right now, but if it comes up in the questions later on, then we can definitely explore that further. So, all right, so let me just zoom in a little bit on the runtime, because most people who start developing on Substrate are most interested in developing a runtime. That's to say, if you want to build a blockchain, you probably have some application in mind, or, you know, you might call it a DApp or a decentralized app that you want to build, and most likely you'll end up building that in the runtime. There are people who choose Substrate for other reasons. Maybe you have invented some sort of novel consensus algorithm, and so you want to end up coding in that part. And we talked a little bit about that last time as well. But for the most part, people want to build in the runtime, and for that reason, most of the recipes currently are about the runtime. So here we go. Zooming in on the runtime, also known as the state transition function. So if you think of a blockchain as a state machine where it has some state currently, like in Bitcoin, the state would be the, the accounts and what balance is in each account. And then there's some transition function that allows it to change state, to update to a new state. So in Bitcoin, the state transition function is something like you're allowed to spend tokens that you own to whomever you want, as long as you can properly sign the transactions. And so you send one of those transactions in, the state updates, and the balances change. Well, Substrate's really generic. It's not just about cryptocurrencies or about Bitcoin. And although it does that stuff, it actually does much more than that. And so we have this technique called frame for writing runtimes. And what you do is you can choose any of these pallets here. You can say like, okay, what piece of functionality or pieces of functionality do I want my runtime to have? If you want it to have some proof of stake sort of features, you can choose the staking palette. If you want it to have some notion of a pot of funds that's generally used for the good of the chain, maybe for like developing new features or maintaining the chain, you can use the treasury. If you want to use some of this like on-chain governance, you might choose democracy, etc. And so I've listed some popular ones here that come with Substrate, but as you can see, there's also many more. And the real beauty of using pallets like this is that you can write your own pallets. If we haven't described the logic that you want with our pallets that are available, that's great. You can write your own. Most chains will probably use some that come with Substrate and some custom ones that the chain developer wrote on their own. So yeah, right. So like I said, the runtime is the blockchain's application logic. Okay, so that's all great. Now, what can we actually build with Substrate? Let's think of some concrete examples, and then we'll dive into the recipes code and start looking at the actual code. I showed this slide last time, and I'm guessing that people have seen it before. This is the design of Polkadot. So you've got the relay chain in the middle, and then you've got all of these parachains on the outside. And parachains are individual blockchains with their own application logic that share finality by getting their finality from the Polkadot relay chain. So what could we build with Substrate here? Well, one thing we're building with Substrate is the relay chain itself. Parity actually started building Polkadot before they decided to build Substrate. And once we were partway through building Polkadot, we said, hey, we've built a lot of these blockchains. Let's isolate the useful, reusable parts out into Substrate. But it's not just the relay chain. We can also build parachains with Substrate. Now, in reality, they probably won't all be built with Substrate, like I've shown here, but it's possible that they might be, and it's really likely that many or most of them will be. But it's not even just about Polkadot. Although Substrate was born in the context of Polkadot, you really can build any chain you want with Substrate. So you could also have these standalone chains over here that are just doing their own thing, not even related to Polkadot at all. So let's look at it on a Venn diagram, because I love Venn diagrams. On the left side, you can think about all the Polkadot parachains, and on the right side, all the substrate chains. And there's this intersection here. These are the Polkadot parachains that are built with substrate, like we saw in the previous diagram. But like we said, there might also be non-substrate parachains, and there might also be substrate chains that aren't parachains at all, that aren't even related to Polkadot. So Substrate really strives to be as flexible and general purpose as possible. So, all right, here we go. With that overview and context sort of established, let's dive into a project that I really care about and spend a lot of time on, and it's called the Substrate recipes. So there's two links here, and I'll copy them both into the troll box just so everybody can click them easily, and I'll open up both of them and show you what they are. Okay. So there's the first one, substrate.dev/recipes, and that's where you can actually read the book, the Substrate recipes. But the book is just the tip of the iceberg. Here's the rest of the repository. It lives on GitHub. Yep, there you go. And oh, hi, Alex. Nice. That's good. So you're checking it out. So I will start by showing you guys this one, the rendered recipes. Whoops. Okay, and it's a book. It's written with MD book, so it looks like other books you might see in the Rust ecosystem. And you can tell by the table of contents over here, it's a book that's sort of meant to be read in order, but not entirely. And so let me just take you through this here. By the way, there's some really good ways to contribute as well. So if you want to be a contributor to Substrate recipes, that's totally welcome. And as we go through this webinar, you'll see some ways to get involved. So like I said, the easiest place to read the book is right here. That's where we are. And the first two chapters are meant to be read in order. So we'll actually start out by going through some of that. I won't spend forever on it because I know many of you have sort of prepared your kitchen before we got started here. Chapter 1 is about preparing your kitchen. So we'll set up like a Rust compiler. We'll get Rust stable and Rust nightly, and we'll set up that WebAssembly toolchain that we talked about so that we can compile our runtimes down to WebAssembly. And then in chapter 2, that's what I call the appetizers. And in the appetizers, we write a couple small runtime pallets, and they show some really fundamental things about pallet development with Substrate. So we'll go through the 4 of those too. The rest of the book, the entrees, which is by far the biggest part, all of this part, can be read in any order. So the idea is, if I want to learn how to do this like charity or currency imbalances thing, I don't need to read all of these recipes that come first to understand it. I just need to know the basics, and then I can skip right to that one. Or maybe you're mostly interested in consensus, so you want to come down to like this proof of work example. That's fine. You don't have to read all these entrees in order. So the recipe strives to be a place where you can, after you've gotten your footing, you can say, okay, I want to do blank. Let me see a working code example and a write-up that explains how that code example works. And then this is the other link I wanted to show you, and this is the GitHub repo. So oh no, Substrate, oh, we had a typo. Okay, Substrate Developer Hub. Just in case anybody ran into that same problem, let me give you the proper link. Yeah, nice. Thank you for catching the typo. There you go. Okay, so here it is. Here's the repo. And I just want to talk about the structure of the repository a little bit because it'll really help you follow through the recipes. So the first folder to observe here is text, and this is where a bunch of markdown files live. This is where the content that's in the book actually lives. So you can dig in here and look, it makes perfect sense. Prepare your kitchen, appetizers, entrees, and then inside of here is just markdown files. So if at some point today or in your own exploration of the recipes, you're digging through, you find a typo, this is where you fix the typos, and pull requests are totally welcome. You can see we've got a few open right now. I don't typically spend much time in the text here in the GitHub or like text editor interface, except when I'm writing recipes. Mostly I read the text through here, through the rendered book. So the next part is, so we've got three code-related directories: nodes, pallets, and runtimes. And I'll just come back to this architecture diagram and I'll explain why it's broken down that way. So here's our architecture diagram. In the directory that's called nodes, we have Rust code for this entire diagram. In the nodes folder, you'll find entire complete substrate nodes, both of the pink bubbles, all the consensus and everything. Now, it doesn't mean I've written the code for the consensus or the libp2p. That stuff is just Rust dependencies. But what it means is that that's an entire node that you can build and run and start a chain with. So the next directory after nodes is runtimes. And a runtime is just this part here, just application logic. So a lot of times you don't even want to build your own whole node. You just want to build the runtime, and then the node, you'll just take a standard one. Like in the recipes, we've got something called the kitchen node, or we also have this project called the Substrate node template. And in many cases, like I said, you write your runtime, you're good to go. You don't need to write the node yourself. Okay, fine. And the last folder is called Pallets. And so we talked about previously how the runtime is composed of pallets. And so inside of the Pallets folder, we can see a bunch of them. So each one of these, adding machine, basic token, charity, etc., is one individual runtime pallet. And these things can be combined together and composed to make a runtime that does whatever we want. So that's the structure of the recipes. We've got the nodes, the runtimes, the nodes, the runtimes, the pallets, and the text. And then if you're a dev or a GitHub person, this stuff will look familiar. And if not, just ignore it. It's not like the most interesting parts. These 4 folders are the interesting parts. So, okay, so let's go. If you're in this call getting help, the easiest way is to ask a question through Crowdcast. That would be great. Obviously, I'm not always live streaming, so you can get help on Stack Overflow. We use Riot at Parity, and there's this channel called Substrate Technical that you can go to. And then finally, you can open an issue on GitHub. And that's just this issue queue right here on the recipes, this one. And issues can be anything. It can be help, I'm stuck. It can be, hey, I have an idea for a new recipe. It can be, hey, this recipe was fine, but I have an idea to make it better. All of that's totally welcome. And we already talked about what's Substrate, so I'm going to skip that. Obviously, learning Rust is important, and here's some resources if you want to do that or haven't done that yet. So let's dive into prepare our kitchen. This section is going to teach us how to build a node. It's called the kitchen node. It's not our only node, but it's the one that we'll start out with. It's going to show us how to interact with that node and use it and play around with the pallets that come in its runtime. And then finally, understanding the kitchen's organization. So I give you a preview of that, and that's covered here too. So let's see, building a node. If you want to build a Substrate node from the recipes, which I, of course, highly recommend, here's how you do it. There's some prerequisites, and you can get all of the prerequisites with this one-line command. It's going to download a script from getsubstrate.io, and it's going to run it, and that's going to install a bunch of dependencies, like some things that we need to link against. It's going to install Git for you and CMake and just some build tools. There's a special section about building on Windows. If you are on Windows, I really recommend the Windows subsystem for Linux. It's really cool. It gives you a whole Linux environment inside your Windows 10 system. You don't have to use that. We do support Windows, but I will say, most people who are hacking on blockchain are on Linux or Mac at least. And so you'll get more people who can help you, and it's a better trodden path on Linux. So consider it if you're a Windows user. Okay, cool. So here we go. Now we're ready to compile the kitchen node. So this is one of the nodes that lives in the nodes folder. If you haven't already, git clone the recipes. So what that means, I think most of you know, you just copy this link for the recipes, and you go to your terminal, and you can type git clone and clone that. I'm not going to do it now because I've cloned it already, and I'm already in the recipes. But if you haven't, you should. Okay, great. So that means we have the code. In fact, let me just show you that. Here's inside the code that I've cloned locally, and it's all the same stuff we can see. Here's our 4 directories: nodes, pallets, runtime, and text. And some of these like book and target, those are around because I've built the project. Okay, cool. If you just ran this prerequisite script, then you won't have to run init.sh. But if it's been a couple days since you've run that, or if you got those prerequisites a while ago, you can run this script and it will like update your Rust WASM toolchain and everything. And then finally, here's the command to build the kitchen node. So I know most people on the call are devs, but I don't know if you're all like Rust devs or familiar with the Rust ecosystem. So cargo is the build tool and project management tool for Rust. We're giving it the subcommand build, which means we actually want to compile this thing. And then we're giving it the release flag. And that's sort of like the optimized build. Like the alternative is a debug build, which keeps debugging symbols and performs less optimizations. And for Substrate nodes, you typically are encouraged to build them in release mode. And the reason is block authoring can take a long time if you don't do that, and you might miss your build times. So by all means, you're welcome to play around building without release mode, but like when you start to have trouble with block time and everything, like this is the first thing to go to. I recommend release mode. And then the final thing here is -p and the name kitchen node. And so with the recipes, there's a lot of different pieces of code that live in the recipes. Like we saw, there's many different pallets, a couple different runtimes, and a couple different nodes. And so generally you don't want to spend time compiling everything just to mess with one thing. So here we're telling it just build the kitchen node and all of its dependencies. So that command, if you haven't run it before, will take some time. Like it might take 20 minutes or so to build a node from scratch. If you have run it before, then you get incremental compiles and they only, take a minute or so or a couple minutes to rebuild in between. So let me pause again to look at the questions and troll box. Okay, cool, we're doing good. So no questions yet. So when you do have questions, definitely ask them. And until then, I'll keep going. Okay, so let's just see what that looks like. So here I am in the recipes. I can do cargo build release -p kitchen node. Okay, fine. So it's going to download all of the latest, dependencies if any of that stuff's changed. And you can see for me, it started like most of the way done. And that's just because, I built this thing this morning and I work in the recipes a lot. So it's not going to take that long. So now we can see it's building the super runtime. So the super runtime, if we flip back to our architecture diagram, this whole thing would represent the kitchen node, and the runtime that we've installed in it is called the super runtime. So if you want to build the node, you have to build its runtime. And so that's what I'm building right now. Yeah, that's great. So I haven't said too much about it at this point in the recipes, but you can really build anything you want with almost this same command, pretty much anything from the recipes. So I'll let that one finish and then I'll do a demo of that. Once it builds, then I just have this command here. Like if you haven't used Substrate before at all, it tells you, this is a Rust convention. The thing you just built will build to the target release directory. And it's called kitchen node in our case. And I just am indicating that we should run the --help command just to make sure that, our node built and some output comes out. So once I'm done building, we'll do that. Yeah. I guess in the meantime, we can sort of like take a look around here. Oh, in fact, I can open this up in my code editor and we can take a look around that way. So here I am again with all my same 4 directories. And if I go into nodes and kitchen node, this is what we just built. So I always like to look at cargo toml, and you can see there's all these dependencies. Some of these are just like regular Rust dependencies. Many of them are parts of Substrate. So all of these come from Substrate itself. So you can see I have like SC and SP consensus babe. So that means I'm using babe consensus. It was written at Parity. It's part of Substrate. I'm not writing my own consensus for this kitchen node. Same thing with my finality gadget. I'm just using grandpa. Same thing with like, what's another good example here? Like even the CLI, the command line interface, I didn't invent all the sub commands that the kitchen node has. I just took them from Substrate. And now here is where I specify the dependency of the runtime. And you can see I've specified the super runtime. And instead of saying like a version from crates.io or a place to find it on GitHub, I've just given it a path because that comes from the exact same repo here. And you don't have to use that runtime. There's other runtimes that you can install in that same node. Like if I comment the old runtime and instead install the wait fee runtime, I could, I'm not gonna because we just finished building the last one, but I could again run build release kitchen node, and now I'd have the same outer node with a different runtime on the inside. So let me put that back before I forget. And then, okay, cool. So that finished building. And let's just run this command to make sure everything worked the way we expected. Boom. So there's our path, target release kitchen node, and I'm going to run -- help. And if it gives you text like this, then great, you built it. And it tells you, I mean, this is a good command to see. It tells you like everything that this node can do. Here's some of the like useful flags. There's so many of them actually. Here, let's start with this one, -- dev. That's one that I use a lot. And basically what it does is it starts a blockchain, network in sort of the edge case where the network only has one node. And that's all you need when you're like testing out your runtime logic, for example. So, okay, cool. So we built the kitchen node. So let's keep going. Interacting with a node. We just followed those instructions, so we're good. And then it says launch a development node. And that's actually what I was just telling you about. We are going to do this command. But I have this other one first. It says purge existing blockchain data, if any. So when you're developing a blockchain and like making changes to the runtime, you can imagine like any program, you code a little bit, you build it, you run it, and then you're like, okay, let me make some more changes. So you code a little more, you build a little more, and you run it. And if you don't purge the blockchain data, which just means delete all the blocks and the history of the blockchain, then after that first iteration, you'll be running like the new version of the code, but you'll still have the genesis block and the blockchain state from the old blockchain. So if you're working through the recipes for the very first time ever, you don't need this command. But if you're not, you need that command, and it's harmless anyway. So that's why I include it here. It's just a good practice that you'll always run that. So same exact binary we just ran, target release kitchen node, and then we'll give it the purge chain command, and we'll tell it we want to purge our dev chain, and it just says like, are you sure? Great, it deleted those files. So for me, having coded on the recipes on the kitchen node before, it was important that I do that purge chain command. And so now we're ready to just run our blockchain. So path to the binary, kitchen node, and then we'll run it in dev mode. And here we go, hooray. I guess many of you have seen something like this before, but for some of you, this might be the first time running your own blockchain node. So if it is, congratulations. And it tells us a lot of stuff that's going on here. So I recommend as you're going, every time you start a node, spend a little while studying the logs until you sort of become familiar with them. Right now, I'll just point out a few important ones. This style of log, here, sorry, let me make that actually readable. So this style of log comes up every so often. I don't know how often, every couple seconds maybe. And it tells you how many peers you have. In a dev node, it's always going to be 0 because we're the only node there. But like in a live blockchain, you would want to see some peers there. It tells you what the best block you know of is, and you can see it keeps going up, and that's just because we keep authoring blocks, and that's normal and expected. And then it tells you what the best finalized block is. And so finalized means we will not reorganize or discard around that block without a hard fork. So in Bitcoin and other purely proof of work chains, you don't really have a notion of finality. It's the case with Bitcoin. It's unlikely, and there's really good mathematical analysis to quantify how unlikely it is. But it's always possible that a new long Bitcoin chain could come out today that's longer than the one that we all know and love as the Bitcoin blockchain, and like reorganize the last couple days or weeks or months or years of block data. But with deterministic finality, we can see from this log that we're never going to reorganize around that block number 1. And then the caveat is unless you do a hard fork. So as we scroll down, we keep seeing more and more of those logs, and now we're up to 15 finalized blocks. So that's great. We've got a blockchain node running. We can appreciate it here by looking at the logs. Ultimately, though, we want to be able to actually like interact with this chain and submit transactions and everything. And so there's this really useful user interface in the Polkadot ecosystem, and it's called apps, or Polkadot.js apps. And so I'll say before I start, there's this little footnote here, like Firefox doesn't like it when you run this apps user interface and try to connect to a local node. And it's for some pretty good security reasons in general, but it's a little bit of a pain when you're a blockchain dev. So if you're a Firefox user like I am, there's a couple alternatives, like you can host it yourself. But honestly, the easiest thing to do is just choose a browser that doesn't have that security feature. Like I use Chromium, and my default homepage for Chromium is just this apps interface. So here we are, we're connected to our kitchen node, that thing that we just built. You can see we're like 29 blocks deep, and pretty soon it'll say 30. I think every 6 seconds I get a new block. And I always just like to do this real quick and dirty check to say like, okay, the node I ran here is on block 31 and the interface says block 31. So it's pretty likely that this is the same blockchain. So we can do stuff. We could transfer tokens if we wanted to, or what I'll typically be doing with the recipes is submitting transactions, or as they're known in Substrate lingo, extrinsics, through this extrinsics tab, and then reading the state of the blockchain through this chain state tab. So let me just do a little demo, I guess. The first thing you do is select what account you want to use. I'll use Alice. You can see she has plenty of tokens. And then you select what pallet it is that you want to interact with. So you might remember inside the runtime, there's all these different pallets, and here's where you choose which one you want to interact with. So we'll just start with this single value one. And I haven't really told you what it does yet. We can look at this recipe in a second, but maybe for now, I'll just show you how to do this. You choose the single value pallet, and then there's 2 different kinds of transactions you can submit. You can either set an account or set a value. And this pallet doesn't really do anything too high-minded. It just has a storage value that keeps track of some account and a storage value that keeps track of some value. So let's just try set account. I'll submit that transaction and I'll sign it. And okay, so that was pretty fast. You have to wait until the next block comes before your transaction actually goes into that block. And now that we did that, we can come to chain state and we'll select single value. That's the one we just did. And we'll look at what the stored account is. And it tells us it's an address. So like, if you're new in Substrate, you don't recognize that address, 5GRW. But if we go to our accounts page, we can see, it doesn't show it, but let me just copy Alice's address real quick and paste it where we can see it. Whoops. There we go, 5GRW. So that's Alice. So this account that's stored in the single value thing, that's Alice. And that makes sense because she's the one who stored the account. So we could try it again if we wanted to, single value, and we can call it as someone else. Let's call it as Bob this time. And we'll just remember for our own sanity, Bob is 5FHNEW. And we'll submit it. And that one went fast too. We're getting lucky today. Single value, and we read the stored account. You can get rid of those notifications. And 5FHNEW, that's Bob. Okay, cool. So what we've seen so far when you get started with the recipes is right away you can build a node, you can launch a node, and then you can interact with it from this convenient browser-based interface. So let's look back at the troll box here. Why is Babe referenced twice? Okay, that's an awesome question. Thank you for asking that. Let me go back to that spot so I can answer it. So just to reorient everybody, I'm in the nodes folder and I'm in the kitchen node folder and I'm looking at its cargo.toml file, which is where you specify all the dependencies in a Rust project. And the question was, I think about these 2 lines. Why is Babe referenced twice? So why is it referenced at all? Because I'm using Babe consensus. Why is it referenced twice? These are not exactly the same package. The first one is SC, which stands for Substrate Client. So I'll just make some notes here. SC equals Substrate Client. And client is another name for like the outer node, or if we look at our diagram here, The client is these gray parts that don't include the runtime. It's this stuff that's just built into native. So we have SC consensus Babe. That's the part that does the actual like block authoring and all the heavy lifting for Babe. But then we also have this this SP package, and SP equals substrate primitives. And a primitive is basically like a primitive type. So if you think about the dependency graph of a blockchain that, or any piece of software that looks like this, where part of it is built into WASM, where there's no standard or no STD environment, and part of it's built into native, where there is an STD environment, what we really want to do is we want to have these simple primitive types in their own crate. And so any type that's going to be needed both inside the runtime and outside the runtime, that's what we call a primitive, and it goes into this SP crate. And then the actual like Babe like logic, like the block authoring logic and all of that stuff, that's what goes into SC. So we can see here that like we're looking at the node, the outer part of the node right now. It depends on both. If we just look over here at the runtime, so I said before we're using the super runtime, and let's look at its cargo.toml file. It's a slightly different format in this case, but you can, oh yeah, so here we go. So in this case, we depend on SP consensus Babe. That's the primitives. The primitives are needed in both places, but we don't depend on SC, the client code for Babe. Now, as you can see, there's also this thing called Pallet Babe, and that's another whole thing. That is this pallet that goes in the runtime. So with Babe, it supports proof of stake and all kinds of fancy ways to choose who the block authors are, and that gets coordinated through the runtime. And so that's what the runtime pallet's for. So I hope that answered your question. And then, oh yeah, oh cool, and it even answered the next one. What are SC and SP prefixes? So there you go. SC is substrate client, SP is substrate primitives. Okay, let's see, where did I leave off? I think here. Yeah, so great. So we just did all of this stuff. We worked with, you know, the extrinsics and the chain state. And oh yeah, okay, I'm glad we're reading over this, because here's one thing that I haven't said yet. And that's the following. Every blockchain's runtime is going to be different. Like we said, you can build a really wide variety of blockchains with Substrate. And in order to use a single interface like this one, like Polkadot.js apps with all these different blockchains, we need to also tell the interface about the types that are used. So it's actually really good timing to be asking about those primitive types. In order for this interface to work with your specific blockchain, you have to do a little bit of configuration. So if you were following along with me and you got stuck submitting those extrinsics, this might be why. On the settings tab, you always have to tell it what node to connect to. Like by default, I think this thing's connected to Kusama, which is an awesome network, but not what we're talking about right now. So we'll stick with local node. Then on the developer tab, you have to give it all this information about what types your node uses. This is like really analogous to those SP or substrate primitive packages we were just talking about. So at a glance, it looks overwhelming, but it's not. It's actually pretty straightforward. It only looks so overwhelming because this is the super runtime and it has a whole bunch of pallets in here. So let me just show you where you get this information. When you're working with the substrate recipes, you know, different chains handle this different ways, but I think in the recipes, we've got a pretty nice process for knowing where to get the types from. And here's how it works. The types are all about the runtime. So if let me just close the node so we're not confused. If you look in the runtimes folder and then you look in a specific runtime folder, like now we're in super runtime, you'll always find a file called types.json. And this is all the types. So I just copy paste that stuff. Well, copy it. And then over here, I paste it. It didn't change for me, although, you know, in most cases it would. And then you click save. And now apps knows how to work with the super runtime. So imagine we did that experiment I talked about earlier. You know, I already showed you how you can wire the kitchen node up to work with with a bunch of different runtimes. But for example, just this wait fee runtime. So in that case, then I would, close the super runtime folder, open the wait fee runtime folder. Here's its types.json, and it's way shorter. Like most runtimes have fewer types. And so we would just copy that and we would paste it in here. and save it. And now this apps interface knows how to interact with the types in my wait fee runtime. So the types can come from the runtime itself or from the individual pallets. And so just since we're on the topic of types, like if you look into any one of these pallets here, they all also have their own types.json file. So like this charity pallet is simple enough that it doesn't have any custom types. Check membership is also simple enough that it doesn't have any custom types. Compound interest is a little bit more complex, and it has just a few custom types in there. And so when you build a runtime, it aggregates all of the pallets types into this big runtime level types.json like the one that we saw here, and then you can copy it and use it with your user interface. Let's see, I guess I've got kind of a lot of windows open. Okay, yeah, great. So I'm gonna keep trucking here, I guess then. Yeah, so chain state and extrinsics, we looked at all that stuff. So let's look at kitchen organization again. The structure of a node. Okay, we talked about this plenty. Like this is a less sexy version of that diagram that I keep showing you guys. Like here's the client, the outer gray circle, and then there's a bunch of different parts that are inside of it, consensus and runtime and transaction queue. And inside the runtime itself, there's a bunch of different pallets. So that's a figure you're already familiar with. And then here's those 4 different directories that I have also already told you about. So I won't go through that in detail again. I'll just show you this. I think this is an interesting diagram. It's the structure of the recipes. You can see, text, nodes, runtimes, pallets. And it has these things all expanded out a little bit. And so I've sort of indicated which ones you built. So the command we ran was cargo build -p kitchen node. So like, it's no surprise that we built this thing, right? We explicitly said to build that. We've also built the super runtime, and I sort of explained that, the kitchen node depends on the super runtime, so we build it. And then if you look into the pallets directory, we've even built some of these pallets. And the reason that we've done that is because the super runtime depends on some individual pallets. So when you build the node, just like any REST project, it builds all the way down the dependency graph, all the things that are dependent on. So runtime, pallets, even down to like substrate primitives. Okay, yeah, so I already showed you guys this line, like you can comment out the super runtime and add in the wait fee runtime. That all makes sense. Here it says, let's look inside the super runtime. And in its cargo.toml file, we can see where it depends on all of these different individual pallets. So let's just look at that real quick. Runtime folder, super runtime, it's cargo.toml. Oh, that's this one I was working on right here. And you can see here's a couple pallets I just took from Substrate itself, like balances. That's a famous pallet. Pretty much every Substrate chain uses it. It basically just gives you a simple cryptocurrency. Transaction payment, that also comes with Substrate, and basically every chain will use it. You either should use this pallet or write your own equivalent of it. And the reason that you do that is in these decentralized networks, all the people who run the nodes are the ones who are actually paying for the computation that the blockchain is doing. So, like in a more Web 2.0 world, if you want to do some compute on like Google Cloud or AWS or DigitalOcean or whatever, you pay a bill to use those cloud servers. On a blockchain, that gets abstracted away a little bit. It's the node operators that are doing the compute, but at the end of the day, they're still paying for either a cloud server or their own server. And so in order to make your chain secure so that there aren't people who are just submitting transaction after transaction after transaction, like, hey, it's free, I can con these nodes into running my, computing my stuff for me. That's why we have to pay a transaction fee for every transaction. And this pallet, the transaction payment pallet, makes that easy. So anyway, yeah, here's the dependencies from the super runtime down to all of the individual pallets. And then here's a few more dependencies that are just Substrate sort of stuff, things that come from Substrate itself. Maybe we'll just take a look at another runtime real quick, the wait fee runtime, and we'll look at its cargo.toml file. So here is the only pallet that I've added from the recipes this time. This is a much smaller runtime. It only has this one special pallet. I think it also has balances. But the ones that came from Substrate itself, I've just listed down here in this other format. So yeah. Okay, cool. Yeah, this is talking a little bit about where the code lives. So within each, within the pallets directory, within each pallet, then you have a source folder that's a Rust standard, and lib.rs, that's where the main code lives, and etc. So I have a couple of quick links here. These go back to some tutorials on the Substrate Developer Hub, substrate.dev. So by all means, those are good tutorials. So some of them I've written, some of them I just help maintain, but yeah, they're good resources. But we're not going to do them right now. We're going to stay focused on the recipes. And so now that we've got our kitchen set up, we've sort of looked at the structure. We've talked about how to build different pieces. Let's go ahead and get on to the appetizers. So this section is going to cover 4 things. They're all about writing individual pallets, and they're sort of like fundamentals. And once you've got them down, then you're, you've sort of graduated to like intermediate level Substrate dev, and you're ready to be released into the entrees on your own. So we'll definitely be able to get through all 4 of these, and we'll just start with this first one about dispatchable calls. So you can see that's, section 2.1, and I called it Hello Substrate. Like that's, everybody's used to Hello World. So that's where we'll start as well. And before I dive into the text, I just want to point out a convention, which is that there's always a link right after the name of the recipe. And if you click that link, it takes you to the spot in GitHub where the code lives. So you can see now we're already in recipes in the Pallets folder in the Hello Substrate recipe. And then here's the source, and here's lib.rs. This is where the code of your pallet lives. So there it is. Now, like I said, you can read this stuff on GitHub, but the best way to really learn a lot from the recipes is to not just like read the recipe. It's good. Reading the recipe is good for sure. The next step up is to sort of read the code. That's what we're doing here. The next step up is to sort of like compare the code to other code that you've seen, or maybe other recipes, or maybe some code from the Substrate repository itself. And then like the next level, even beyond that, is to sort of hack on top of the recipes. So in addition to just reading them and seeing what they do here, to actually like explore them and mess with them a little bit and see if you can make them do what you want. And so I'll demonstrate a little bit of that today too. So I have the code cloned. I'm not going to read it on GitHub, so I'll just go ahead and close that. And here we go. The first thing it points out is this line about no STD. So pallets live inside the runtime. Here's our runtime. All the pallets live inside of there. And because it compiles down to WebAssembly, that means we can't use STD, or the standard environment that comes with Rust. So the first thing we do is we tell our pallet that. So let me get back to that same spot we were at. We were at pallets, and the specific pallet we were at was called Hello Substrate. So here it is. There's the source folder, and there's its lib.rs file. Oh yeah, I think the changes there were those notes I made about SP and SC, so I'm not going to save those. So here's that line. It says, unless we're building with this STD feature, the default is to compile down to no STD, and then I've got some comments. Okay, great. Where's the book? There. So next thing you'll see is some imports. Okay, great. Let's look at them. Here they are. Every pallet's going to use frame support because that's where these macros come from. We'll start with decal module. That's what this recipe is about. Every one of them is going to use frame system because system is just necessary to write a pallet. Not all of them will use this. In fact, most of them won't use this print one, but that's what we're doing here in the Hello Substrate recipe. Okay, good. So if you've programmed Rust, those should look familiar, and if not, they're pretty straightforward. You just say use, and then you say what features of each dependency you want to use. Next up, I configure my tests module. So testing is super important in development work. It's probably not the first thing you learn, so we won't dig too deep into it in the appetizers, but just to point out it a little bit, it's our goal that every one of these pallets will have a tests module. Right now, most of them have that, but not all. And the tests live over here in tests.rs. And these are really interesting. There's a whole recipe just about writing tests, but like I said, let me not get derailed on that right now. Okay, so we've been through the no STD part. We've been through the dependencies. We've said there are tests. We haven't talked about them yet. Next thing that every pallet needs is a configuration trait. This should probably be commented. This pallet's configuration trait. And this one, since we're starting simple, since this is hello substrate, this trait is itself dead simple. You can see it's actually empty and there's nothing in there. In general, in more complex pallets, you'll have a bunch of associated types that you need here. So like almost all of them will have type event and put some trait bounds on it. And then, you know, you might have, if your pallet is going to do anything that involves money or currency, you might want to have some notion of currency. So like, you know, currency, you could do something like that. But like I said, we're not there yet. And this pallet is pretty simple. So it just has an empty configuration trait. Cool, no big deal. And then the final thing that we're going to see in this pallet, our very first pallet, our very first appetizer, is the decal module macro. Okay, so if I flip back to the book here real quick, whenever you read through it, you know, I might not say all of these as I'm talking, but whenever you read through it and you encounter something like the decal module macro, you know, it's a pretty natural thing to be like, what the hell is the decal module macro? So these links, you know, anytime you find like encounter a new trait, a new macro, a new structure, or any of these things that come with Substrate, you can always click on it and it's going to take you to what we call the Rust docs. So if you're familiar with the Rust ecosystem, this will look super familiar. This documentation, oh, this one is like a lot different than how most of it is. Here we go. This is looking more normal. These documentations will show you like how this particular macro works and give you a lot more jumping off points if you want to know like how does this relate to other macros or what structures does this create, for example. So I'm not going to go all the way down the rabbit hole of decal module right now, but the point is as you're going through the recipes, we generally stay focused on one thing. Right now we're focusing on this like hello substrate thing, but there's lots of jumping off points for when you want to learn more or learn about something that's you know, mentioned here. Here's another great example. So like each one of these inside the decal module macro, we put a whole bunch of functions here. Ours only has this one function, say hello, but there could be plenty more dispatchable functions. And in general, there will be multiples of them. And so we can see that each one of them returns this thing dispatch result. And so what I recommend is as you're going through the recipes, start by just doing the way it does it here. You know, if it says like, okay, you need to return dispatch result, great, return dispatch result and get something that works. And then when you're ready to learn more and say like, okay, well, what is dispatch result? Why did we return that? You know, what's its type definition? Here's another one of those links that takes you to the Rust docs. And it'll tell you all about it. And like, oh, look, it's just a type alias for Rust's normal old result type and a specific kind of error known as dispatch error. Okay, awesome. So yeah, so I guess just to look back at our code, we have our decal module macro. This part I just think of as syntax that you always type. It looks funny. It looks like it's kind of, you know, not very normal Rust, and that's because we're inside a macro, but you can just put it and it works. And then here, these look way more like normal Rust functions. And I think I used the term earlier called dispatchable call. And what dispatchable means is this thing's a transaction. When you submit a transaction to your blockchain, it has to be some particular kind of transaction. And one kind of transaction is say hello. So like in Ethereum, one kind of transaction is an ETH transfer. Another kind of transaction is to deploy a contract. A third kind is to call a contract. Well, in this particular pallet, there's only one kind of transaction, and it's this say hello one. So here's what we do inside. We use this ensure signed function, and it takes this only parameter. The first parameter in one of these things is always called origin, and origin represents who called this function. And when you start out by saying ensure signed, that means ensure that whoever called this is just a normal user of the blockchain. Like they called it by submitting a transaction. And then ensure signed, first of all, it ensures what I just said, that it's a normal user. And then it also gives you back who was the user. Like earlier, we were calling as that Alice account or that Bob account. And so in those cases, caller would be Alice, for example, or caller would be Bob. In this case, like we haven't done too much with caller. Well, we'll get there. So our simple hello substrate one does one thing. It prints hello world. Now, if you're a Rust programmer, you might notice that like this is not how we print, right? In Rust, you normally do this print line macro, and you would do hello world like this. But the problem is print line, this macro, comes from standard environment, comes from STD, and we're in a Substrate runtime right now, so we don't have access to that. In fact, let's see what happens if I try to compile this. Oh, let me kill that node real quick. So we could do like cargo. So before I showed you guys how to do cargo build, and that's the command you have to use when you want to compile something. But you can also save a lot of time by doing cargo check, which will just do all the type checking stuff. This is basically asking cargo like, hey, would this thing compile successfully if I wanted to? And it saves at the time of actually generating the bytecode. And since sometimes these take a long time to compile, it's just a nice trick to know. So we'll try like cargo check -p, and then I'll call, I think this one was called hello substrate. And when I just enter the command like this, it's gonna build with STD involved. Because I'm only building this one package. And so my suspicion is that in this case, this is going to compile just fine. And then what we'll see is when we go to build the runtime, it's actually going to fail, because with the runtime, that's where the build script says, hey, build this thing to no STD. Yeah, okay. Hopefully that won't take too long. In the meantime, I'll take a sip out of my, oh, my camera's not on. I was going to show you guys my Harry Potter mug. Okay, great. So it built. That's fine, because we built it to like the STD environment. And then if I do a similar thing, I can do cargo check -p, and this time I'll build the entire super runtime. Oh, whoops. Oh, that's gonna, okay, well, we'll do something else in the meantime, but I think it's gonna fail, and it's gonna say like, hey, you can't use print line because you're not in an STD environment. So that's why we've used this SP runtime. So remember, that's substrate primitives that are designed for use in a runtime. And it has this special print function, which basically all it does is it like relays the information back to the outer node and says, hey, outer node, you're built to STD, you print this message. And then we demonstrate here another way that you can print text which is with debug info. So yeah, okay, great. So here's our compile failure, can't use print line, exactly as we expected. Okay, so let's just demonstrate this thing. Like, we already built our kitchen node. This hello substrate thing is built in the kitchen node. So let's just run it again. Target, release, kitchen node. Remember, it's always good to purge your chain. Might not be truly necessary in every case, but it's always good to have these good habits sort of like in muscle memory. And okay, so we'll use it from our interface. If you remember, extrinsics is where you call those things. So we'll choose our hello substrate palette, and we'll say hello. That's the only dispatchable call. You might remember there's only one of these things here. And so that's why I only get that one option in my dropdown. So let's call it. And it takes a while to go into the block, or 6 seconds, however long it takes to make the block. And there it is. And if we look up here, we can see, here we go. Request sent by that long public key, and then the beginning of the address, 5FH new. And if you remember, 5FH new is Bob. That makes sense. Bob's the one that called it. Let's do Alice. And we'll see sort of like the same thing probably. Yep, there it is. Request sent by, there's her address, 5GRW. That's Alice. Okay, so you might be wondering, we never actually saw this part, right? We definitely saw these requests sent by that particular caller, but we didn't see this hello world thing. And there's a reason for that. And the reason is when you use that SP runtime print function, it doesn't show up all the time or by default. It only shows up with this special flag, this one. When you run your node, if you want to see those, you have to use this -l runtime equals debug. Now, it might seem like, wow, that's kind of a pain and a lot of hoops to jump through just to print a message. But if you think about it, printing messages to the terminal is not really what a blockchain node is about. You know, that's what a CLI app is about for sure. But ultimately in a blockchain, what you're going to be doing is mostly not printing to the terminal. You're mostly going to be doing stuff like updating the blockchain state and emitting events and things like that. So we'll just show this real quick. Okay, so now we get, you can see like from this blue here, we get, we're in debug mode now. So let me just call that extrinsic one more time. So that was hello substrate, and we'll call say hello. And oh, cool, another fast one. There it is. Debug runtime hello world, and then here's the same one that we always saw. That one came from Alice. So, okay, so cool. And with that, you have cooked your first appetizer. Hooray. Oh yeah, this is a good thing to talk about too, that I didn't talk about yet. So let me get to the code. Here's our hello substrate palette. That's the one that I just code toured you guys through. Luckily, that one was pretty short, only 34 lines. What I didn't really do was look at the cargo toml file very much, and there's some interesting sort of STD related stuff going on here. So you can see we've set our default features to include STD, and that means like if you don't explicitly say otherwise, it should build to STD, and we saw that it did when I just ran cargo check -p hello substrate. It built to STD, but when the runtime depends on this palette, it says default features equals false. Okay, so we have to then do this thing where we create this STD feature, and for every one of the dependencies, again, this is a simple palette, so there's only 4. For every one of the dependencies, we have to say default features equals false, and then we have to say if we're building this palette with its STD features, then also build all of the dependencies with their STD feature. So it's one of those things where when you first start, you're like, wow, that seems confusing and like a pain. And you know, you're sort of right. And then eventually, or not even eventually, like pretty quickly, you get to the point where you're like, okay, well, it's pretty systematic. I'm not that worried about it. Like if I wanted to add another dependency here, like maybe I want to include pallet balances, you know, you're probably used to doing something like just saying where it comes from and like what version. That's all fine. But what you might not be used to is, okay, just remember to type default features equals false. That wasn't so bad, and it becomes totally muscle memory. And then also remember to do let's see, pallet balances /std here. And that says only when we're building this hello substrate thing to STD, then also build pallet balances with its STD feature. And it's really common, like you see this error all the time, and honestly, no matter how long you develop with Substrate, you still do it every once in a while, where you do something like this, where you add a new dependency down here, and you forget to add it in this like STD feature up here. And then there's this really common error that you'll get, which I'll just show you. Yeah, I'm not really sure why it wants to rebuild so much of the dependency graph, but it's not that big of a deal. But the error message is a little bit obtuse. It's like duplicate lang item, and it's usually out of memory and something about panic. And what that means is that like somewhere you forgot to either put default features false in here, or you forgot to like, you know, put the corresponding line up here. So that's just an easy thing to watch out for. So yeah, great. Let me check the control box here. Ooh, yum. Yeah, nice. Okay. Oh, yeah. TP says, I thought these functions should not have a return type. Yeah, so that's actually a really nice observation. So let me show you what's going on here. I don't know what I changed, but I definitely don't want to save it. So strictly speaking, these functions do need a return type, and it's this return type dispatch result. But TP, what you're thinking about is actually totally right, and it's totally acceptable to omit the return type and then omit the explicit return of OK. And the reason that you can do that, I mean, the reason you would do it is because it looks simpler and you don't have to, you know, have this. I tend to prefer to keep it just because I like stuff that's explicit instead of implicit, but it's totally a preference of style, and the code in the Substrate repo tends for this style where there's no explicit return type. But anyway, what happens is part of what this decal module macro actually does when the macro expands is if you haven't specified a return type there, it's like, well, this is a dispatchable call. Obviously, I know it has to return a dispatch result, so it just like adds those pieces in for you. And it's a totally fine and acceptable thing to do. So here's that error I was trying to show you guys earlier. Oh, wow, that's uglier than I was expecting. Okay, it didn't print quite the way I thought. I thought it was going to tell me duplicate lang item, but yeah, it failed somehow. And so the thing to remember, the point I was making there was about when you add a new dependency like this, you have to also add it to your std feature only, and remember to do default features false. So I think I want to discard all of these changes so that I don't get my directory too messed up. Everyone please check Ethereum. Oh, okay. So let's see. We did the hello substrate one. Okay, let's do single value storage. So this is actually the palette that we played with earlier before I even dove into code and was just showing like, you know, how the interface works. So now that we've got a little bit of context, let's dive into the code here. And actually, maybe I'll show you the entire code first. So that one was called single value, I think. Or yeah, there it is, single value. So same structure as always. You've got your cargo toml. This one has the same 4 dependencies as last time. You've got your types JSON. This one doesn't have any interesting types. And then you've got your source directory with lib.rs. So boom. Okay, how much of this do we recognize? Well, that's straightforward. We already talked about how the runtime builds to no std. Here's our uses. Oh, whoops, that's a wrong kind of dot comment there. We've got our uses. There's only 2, those 2 that I said you'll always have. Last time we had an additional one to bring in that special print function. This time we're not even using that. We have a test module that I'm not going to look at. We have the same simple configuration trait. It's just empty, just like the last one. And here's something new, decal storage. So this is the first appetizer where we're actually going to look at like storage values. So storage is when you want your blockchain to keep track of something in between blocks. Like you want some state that you've computed to stick around until the next block. So in Bitcoin, the storage is like the UTXO set, or, you know, like if you're not that familiar with Bitcoin, it basically means like what everybody's balance is. That's the storage item. Or in Ethereum, this would be like the state of the EVM, all of the individual contract storages. So in this simple palette, we're going to store 2 different we're going to have 2 different storage items. One I just called stored value. You know, sometimes on these minimal examples, it's hard to think of like creative names. So the syntax here is just use the decal module macro. This line is kind of like syntax that you always copy, like I said before, just like this line. The one thing you do want to change here is that this should be named something at least sort of meaningful, like basically the pallet's name, you know, like call it like, you know, my pallet, or like something even better, something descriptive. So that's why I called it single value here. And the reason why you need to do that is like a little above the level we're at so far. It's just so that you don't get like storage key collisions. So if you had another pallet that used the same exact string here, then you run the risk of its storage items colliding with your storage items and overwriting each other. And that's a mess. And part of why Substrate's so nice is because you don't have to worry about stuff like that as long as you just like put some meaningful name here. So anyway, the way you read this is that this is the name of my storage value. Let's start with the simplest way to do this. So this is the simplest that these lines could possibly look. The name of a storage value and then a type annotation. So stored value has type U32. Stored account has type T account ID, and that's a substrate type that just means like some caller's address. Like for Alice, that was the 5GRW, or for Bob, it was the 5FHNEW. Okay, but then each one of them had this additional little bit of syntax. And, you know, again, this is a macro, so we kind of invented our own syntax here, but all it does is it makes a getter function for you. Like you can imagine if you have this storage value, you're going to want to be reading that storage value sometimes. So this is just a quick way of saying, hey, please make me a function in this palette that's called stored value, and it returns whatever this U32 is. And then same thing here, this like helper function called stored account just returns whatever the value that's stored in here is. So here we have actually just declared 2 storage items. And now we're down to our decal module macro, which we've seen before. So we use the macro, we use this line that I said is just syntax that you always type. We've got a function, it has a name. Just like before, it takes it takes an origin. That's whoever called this thing. And then it takes an additional parameter this time, and I just called it value, and value has type U32. And it returns a dispatch result, and just like we talked about before, it's totally acceptable to do it this way too, if you like. Rust, or my editor doesn't know how to syntax highlight it as well, because I don't really know why, but whatever. So, oh, it wasn't even because of that. Yeah, I don't know why that didn't turn purple, but no big deal. So in this case, we're still using the ensure signed function, just like we did before. That means like I want whatever origin called this to just be a user from outside the blockchain, someone who's just like submitting a transaction here. This time I didn't actually care who it was. Like in the last example, I was going to print that message that says hello to them, so I needed to know who it was. This time I didn't care, so I didn't even bind a name to that variable. And one thing I learned in the meantime actually was that like you actually don't even have to do that let underscore equal. You can just call ensure signed. So now we've cleaned up our code a little bit. Hooray. First of all, by fixing that dot comment, and then second of all, by cleaning up that line. Okay, so let's look at what this thing does. Okay, it makes sure that a regular user called it, great, and then it writes to the storage value. Write the supplied value into blockchain storage. Okay, cool. So it says stored value. That was the name of our storage item. And then we call this associated function put, and we give it the value that we want to put in there. And that's it. And then we return success. And then down here, it's almost exactly the same. But when we call set account, we're not specifying the account to set in the same way up here. Like we said, hey, like the value is blank. I passed in a parameter. Here, set account is just keeping track of like whoever actually called this thing. So you can see in this case, I'm calling ensure signed, and I am keeping track of who the signer was. And the reason I'm doing that is so that I can then go ahead and write this value into storage. So we could actually like use the same comment here if we wanted to. Now the syntax is really similar. We still have this put method that we're calling. You'll notice that we need the generic parameter t here though. And t refers to trait, and it's like, well, what the heck is trait? Well, if you remember, that was the name of our configuration trait. So what I recommend is at this point, don't say to yourself like, oh, I can't go any further until I understand all of this like configuration trait stuff. I think a better way to learn is just to remember for yourself, like primitive types or types that you declare right here in the palette, you can just use the storage values name. But if the type somehow has something to do with like substrate trait, you know, in a little bit, we'll see how you can take those in your own configuration trait, or if it just like comes with substrate, and like pro tip, those come from this system trait, then you need a T there. That's what I would recommend remembering. You just put the T there and then it works. Okay, fine. Yeah, I guess I didn't have anything else to say about that. So we already ran this one, you know, so we saw how it worked. Maybe I guess we didn't do the set value one. Oh, this is something useful to see too. So this is our user interface, and right now it's giving you this not connected to a node error. Well, that makes total sense because I killed my node. So if we just like run the node again, then everything comes back like normal. And I guess we can just real quick do this one, and we can say set value, and maybe I'll set the value to 42. And so set value was this. I called it with value equal to 42. So it ensured that a user called this. It was a user, it was Alice. And then it put 42 into that storage value. And if we want to double check that it actually did it, then we come up here to change state, and we go to single value. And oh yeah, and now is a good time to mention also like what shows up in these drop-down lists, like what things can I read here? Well, that's your two storage values. We can either do stored value or stored account. And in this case, I want to do stored value. And maybe if everybody just wants to make a hypothesis for themselves, what stored value you think is going to come back out? Boom, 42. I'm not going to spend time doing it again. I'll let you guys experiment on your own with doing it again. Just check the troll box real quick. Okay, so there's one question officially here. Oh, from Alex, please explain this weight business. Yeah, right. That is a great question. So I haven't encountered that yet, and I'll make sure that I do before the end, Alex. In fact, we have a whole recipe about that specifically, so I'll get there really shortly. Let's see, where were we? Here. Yeah, so we talked all about declaring storage. Oh yeah, there is one other thing I was going to talk about, and that's this put method. Like it makes sense when you see it. Okay, sure, you call the put method to put a value into storage, but like there's a bunch of things I could have thought of naming that. Like it could have been called set or insert or save or something like that. So the question is like, how do I know that that's called put? And for more advanced storage types, like how do I know what the interface is there? So you can see under this section, reading and writing to storage, just like I promised earlier, whenever we introduce one of these new traits, like the storage value trait, you can click on it and it will give you some of these Rust docs. And then boom, here's the whole interface. Here's put, that's the one that we use. Store a value under this key into the provided storage instance, great. There's also set, store a value under this key. Let's see, this uses the query type rather than the underlying value. I'm gonna be honest, I don't really know what that means. And that's okay, you can get really far in Substrate without knowing what everything about it is. And then here's another one that you're definitely gonna wanna use frequently called get in order to read a value. There's another one called exists. So like sometimes when your chain first starts out, storage values might be empty, and there might be extrinsics that say like, okay, take the old storage value and double it and write the doubled value back to storage or something like that. But you don't want to do that until you've confirmed that the old storage value exists. And if it doesn't, then you throw some kind of error. And speaking of errors, that's our next appetizer. So this one's called adding machine. And okay, here's the first time we encounter this phrase that you'll see a lot in Substrate development. Oh yeah, this used to be somewhere else, so I haven't mentioned that before, I guess, at this point. But it's called verify first and write last. So here's what it means. Imagine that something could go wrong, like there's a way for one of your extrinsics to fail. And I just gave you an example, like if what your Pallet is supposed to do is read a storage value, double it, and write it back to storage, well, that could definitely fail if there isn't a value there in storage already. And so the idea is when you enter one of these dispatchable calls, you check all of your preconditions first, and you make sure that all your assumptions are true. And if not, you return dispatch errors. And only once you're sure they're true, then you can go through and start actually mutating storage and stuff. And the reason that it's important to verify first and write last is because if you don't do that, you could end up like writing to storage first. Like maybe I start going through here, and what I want to do is like record who last doubled the number and then actually double the number. And if I record the person who called the extrinsic first, and then I find out like, oh crap, there's no number to double, then I'm in trouble because I've already updated the storage and overwritten the old, value of whoever called it last, and I haven't actually updated the number. So yeah, so that's the point. Check your preconditions first. So in this recipe, or in Substrate pallets in general, you get to declare all the different types of errors that can happen. And just like we saw with decal storage and decal module, there's this decal error macro, and here's what it looks like. So decal error, there's a line that pretty much always looks the same, and then we start writing all of our variants. And a variant is just like one of the options that this error could be. So this example is an adding machine. Oh, it might actually be the I forget what it is. Let's look at the code. So inside of Pallets, we have adding machine, awesome, librs, and it has a couple functions. Here's one called add, and it says, okay, first check for unlucky number 13. So this is an example of verify first, write last. So like this is sort of a silly contrived example, admittedly. But if the rules of our palette are, hey, we don't ever want this value to be 13, well, you better check first that it's not 13 before you start mutating anything. And so we just use the ensure macro for that. And we want to ensure it's not 13. And otherwise, here's the error that we admit. And it looks sort of similar to when we were writing storage. Like you always write error, and it takes this generic type T parameter, and then you write one of your variants, unlucky 13. That came from right here. So fine. Okay, so now next, we're going to check for overflow while we're doing this adding. So let's look at our storage values. There's a single storage value called sum. You can see there's a getter function, which is also called sum, and this thing has type U32. And so we're going to call this this sum function. So that says, give me the old sum. We're going to call checked add, which means try to add it to value to add. And that was the parameter, right? This one, val to add. So it says, take the old sum, try to add it to this new thing. And then we use a match statement here to say, like, okay, if checked add comes back with sum, that means great, it added correctly and we got a value, and we can use it. But if it comes back with none, that means the addition overflowed. And that's bad in blockchains in general. That's been the cause of a whole bunch of errors, from like exploits in the early days of Bitcoin all the way through the EVM. Watch out for overflows. So here's where we emit our error, sum too large. And then, otherwise, now that we've done all of our checks, we've verified first, now it's safe to write last, to write the new sum into storage. So that's cool. Let's see. Another method of error handling. Oh yeah, right. So up here, I did this the longhand way with a match statement. There's sort of a shorter way that you can do this, where you do it like this. It says using this fancy okay or method. So I still do the same thing, get the old sum, try to add the new value. And instead of matching on each case, you can just say like, okay, either this thing came back as sum, in which case, great, unwrap that and just give me the result back. Or if it came back as none, we need to error out, and here's the error. So that's essentially the same as what I did above. And finally, we have this reset function, which there's nothing we need to check in advance there. We just set the sum back to 0. So let's play with it a little bit. Adding machine. We're on chain state right now, but let's just check while we're here. Okay, great. It started out with 0. Adding machine, and then we'll add like, we'll add 10, and that should work. My hypothesis is that it will work. And then we'll try to add 13. And okay, look at that. Extrinsic failed. Hooray. That's what we wanted. We wanted that to fail because 13 is, it was forbidden. It's our unlucky number. But then we can try to add something else like 20, and maybe we'll just do this add alternate this time, just so we get to try them both out. And okay, so I've added 10 and 20, but not 13 because that one failed. And then we'll just check our storage real quick. Boom, 30. Okay, so that worked exactly as we expected. There is one more appetizer here, and it's called event. It's about events. I'm going to skim it because I want to get on to Alex's question and hopefully have you guys answer more questions or ask more questions that I can answer. This particular recipe is about 2 different pallets, and it's not very common that we do that, but sometimes when there's like 2 different concepts that are super closely related, we do them in 2 different pallets. And here, the distinction is just about whether your events use simple types only, like primitives like U32 and, stuff like that, or whether they actually use some of those generic types, like we saw T account ID earlier. So some prerequisites. This is actually the first time we use the configuration trait. And whenever you want to use events in your palette, you just put this line. It's the same line every time. I'll say it's almost the same line every time. It looks like this when they're simple events that use primitive types, and it looks. I didn't quote it both times, but in the code you can see it looks slightly different when you're using generic types. So maybe let's just take a look. So the first one was called simple event, and so here you go. I'm just going to copy this line actually so we can compare it and contrast it, because like I said, hacking on these and comparing them to each other is a really great way to learn even more. And then the other one is called generic event right here. And I'll just like this is the part where there's a difference. Like I can even make these line up. So the only difference is if you're using a generic event, then event is parametric in some type, and that's your trait, so you put self here. But again, like I've said about a couple other things, as you work with Substrate, this stuff starts to really make sense, and you'll know Rust's type system well enough to know where it comes from. But don't feel like you have to like thoroughly understand the differences between these two lines before you can go any farther. Just remember, like, you know, I'll just copy paste it from the recipe, because that's what the recipes are for. So I guess like I'll just show you real quick this decal event macro. So big surprise, just like there was decal error, decal storage, etc. There's decal event. It has a line that I've broken up stylistically here, but you know, is essentially boilerplate every time. And then here's all of your variants. And you know, like it's a good idea to write doc comments on here. Some input was sent. Cool. Yeah, great. So maybe actually what I'll do right now is like, you know, as I've looked through this code a little bit, I've noticed just a few different little tiny things that I've cleaned up. So maybe what I'll do is actually show you guys how to make a PR, because I would really love it if people were willing to contribute back to the learning of everybody. So here I am in recipes. You know, we can call git branch. That shows all these different branches. Like, you know, if this is your first time using the recipes, you'll only have master. Obviously, I work on the recipes all the time, so I have a bunch of them. But we'll start by just making a new branch. And maybe you have an IDE that you like to make new branches with. I happen to like doing it this way. So I'll make a new branch and I'll call it, my convention is name it after whoever's making the change, and then something meaningful. I'll just call it like little cleanups. And so then I'll commit these. So like, what did I do here? Looks like I added comments to single value. Nice. And I'll commit that and sign it. And then there's this one, comments to generic event. And I'll publish my changes. And so like, I think many of you guys are probably familiar with pull requests on GitHub, and like major street cred to whoever comes and reviews this pull request that I'm making and approves it. It should show up in a second. There we go. So I'll just say like, comment improvements, some stuff we found during Crowdcast. So like, yeah, you guys probably didn't need me to like demonstrate how to make a PR, but the point I'm trying to drive home is like, this is a repo for everybody. It's here so that we can learn from each other, and your PRs are totally welcome, and so are your reviews. So, all right, let's get on to what Alex was asking about, this weight annotation. And like I said, there's a recipe specifically for this, and there's actually sort of two recipes, one that sort of builds on the weights one. I'm not seeing it right now, so there we go. Weights for resource accounting. So I mentioned briefly earlier that in your blockchain, you don't want transactions to be free, because if they're free, then some malicious user will come along and submit 1 billion of them, and the nodes in your network will have to pay for that compute. And that means your chain will be attackable, and the nodes will say, hey, I'm not paying for all of this compute for free, I'm out, and then you don't have any nodes and you're back to being centralized. So that's exactly the kind of DOS thing that I was saying here. And yeah, like, so you might have heard, you know, if you're familiar with Ethereum or the EVM, every opcode has some gas price. And if the gas price is too low, then, you know, that's too low is better than free, but it's on the same spectrum as free. And the point is, people will execute denial of service attacks on the chain. So this is the annotation that Alex was asking about. And there's not that much context here, but this is one of those dispatchable calls. So this is inside of decal module. And essentially what I'm doing is I'm annotating this call with some weight, and the weight is supposed to represent how much time it takes or how much compute it takes. Recently, I saw Gav clarifying that it's specifically about time, but you know, in general, we're going to want a way to quantify all of the resources. Anyway, so it's about how much time it takes for one of these nodes to execute this transaction. And if it's computationally expensive and it takes a lot of time, you should assign a lot of weight. And if it's, cheap and doesn't take much time at all, then great, don't assign a lot of weight, but still assign some. You don't want it to be free. Now, I will say, like, qualitatively, this system is fairly well fleshed out. It works for sure. Quantitatively, we don't really have good guidelines about what like concrete numbers you should assign for weights. But the good news is there's benchmarking going on Polkadot right now. Like, Polkadot is probably the highest profile chain that's being built with Substrate. And so we're doing, like, my colleague Sean is doing careful analysis of like exactly what the costs of running each extrinsic are. And then that will inform our recommendations for assigning weights. But like, okay, so qualitatively, this works fine. We can just press right on. So that's the deal. We want to assign weights to all these things. And in many cases, your extrinsic will take the same time to execute, or very close to the same time to execute, time after time after time. Like the ones that we've seen so far, the one that just prints a message to the terminal, or the one that reads a storage value, adds something to it, and writes it back to storage. Those kinds of extrinsics, they take the same amount of compute every single time. And in cases like that, Substrate comes with this thing that you can use, simple dispatch info. It's an enum, and it has this variant called fixed normal. And, like, there's some jargon there. Normal essentially just means like a normal extrinsic. I'm not really going to dig into the difference between normal and operational here, but fixed means that it's constant weight. It means every time I call this store value extrinsic, it's going to cost 100 weight. That's like how much compute it takes to execute this thing. So yeah, let me just look at some more of these snippets. I guess this gets into complex stuff right away. So like, let me pause and say, like, although we're only a little bit into this bit right here will suit many of the use cases. Like, I don't know, maybe half or something. For more complex transactions, custom weight calculations can be performed. And in that case, what you might want to do is you might want to consider the parameters that are being passed into the function. So for example, like if I'm passing in a vector as, this is not what I wanted to point at, but like, okay, imagine if instead of pointing in a single entry here, like a single U32, imagine I'm passing in a vector or a list of a bunch of U32s. And the idea is we want to add up all of these and then assign that to runtime storage. Well, obviously the amount of compute you're going to do there depends on how long that vector is. The more items in the vector, the more compute it's going to take. And so you might want to take a look at this parameter in order to calculate, the weight to annotate. So there's some traits you need to implement when you're writing one of these custom ones. So, again, like I said, use the simple one when you can. And when you can't, now you have to write a custom one. So you need to make some kind of struct. So like here, I did this one pub struct conditional. I think it's, you can see already, it's going to be just some, it's like an if. And it, has this type parameter here. This is, so yeah, the deal is you're going to put the types that come from your extrinsics in the type parameter list here. And then there's a couple traits we need to implement. One is weigh data. That's the interesting one. That's the one I'm showing in this first block. The other one is classify dispatch. That's implemented here. And that's the fixed versus the normal versus operational thing I was talking about. Operational is, I honestly don't have that good of a sense of it, but it's something to do with like transactions that are like internal to the blockchain or somehow like necessary for its operation. Those can be classified as operational and they get some special fee rules. If you, like anything, if you want to know more, and in this case you might, because I didn't explain it very carefully, you can just click on that and it'll take you to the trait and it'll explain, what the difference is between the two. And it's going to return a dispatch class, and I think that's the enum. Yeah, there's normal and operational. So what does it say here? This is typically only distinguishing normal user-triggered transactions and anything beyond which serves a higher purpose to the system. So interpret that however you want. I'm just sticking with normal here in the recipe. And then the last trait you need to implement is this one called pays fees, and it just has this one function which returns a bool about whether calling this extrinsic should require you to pay fees. And, you know, again, unless this is some kind of really special extrinsic that for some really good reason you want it to be free, and you probably don't, then just return true here and like have it actually pay the fees. So that being said, let's just go ahead and dig into this one here. So this way data trait, the sort of interesting one that I was talking about, it has a single function also called way data. And then it takes this, this parameter here, which okay, so yeah, if you're a good sort of experienced Rust programmer, you'll notice destructuring here. Basically, the parameter is a tuple. Its first element is a bool, and its second element is a U32, or actually reference to a bool and a reference to a U32. And I destructure it to bind names to them, and I call the bool switch, and I call this value value. And what it does, the reason that we're doing this is so what I didn't say is these are the parameters that we're weighing. Like, we're going to attach this way data thing to some extrinsic that takes in two parameters, a bool and a U32. And so this is how you get to inspect the calls to the function. And so, you know, now we can write whatever logic we want in here. If that thing's true, then, you know, great. We'll take the value and we'll multiply it by like whatever constant we put inside of our conditional struct here. Otherwise, if the bool is false, if this thing was false, then the weight is just going to be, you know, we're not going to multiply whatever was in here, this 0th element. So like, yeah, that's where I feel like we're getting a little too abstract while we're just looking at the code. And so that's why I always like to say, while we're looking at the text. So that's why I always like to say, you know, like, let's dive into the code here. So let's close these two. And we were looking at weights. So, okay, so here it is. And there's more examples in here actually than the text. So you can see there's a few of these things. I introduced one of these scales that I just called linear, and then I implement the 3 traits for it: impl way data, impl pay fee, and impl classify dispatch. And then here's another one, quadratic. And this one has 3 you know, values in the struct. And you know, you can imagine if you know what quadratic means from math class, it's like, oh yeah, here's the formula, like ax squared plus bx plus c. These are the a and the b and the c value. So that's why there's 3 values there. And then I implement the 3 traits: way data, classify dispatch, and pay fee. Here's another one. This is the one I showed in the text, conditional, and it implements the 3 traits. And okay, fine. So now we're finally back to some code that you probably recognize from the appetizers. This is where we write our dispatchable calls. And hey, this is a really similar one that we've actually seen before, right? Where we just store a value. But the difference is we've annotated it with this weight, just like Alex was asking about. And this is because it's a dead simple one, because we just do a single storage write every single time. We've just given it a fixed normal weighting, which means it always is going to weigh 100. Now, like I said, 100, that might or might not be the right value. The quantitative part is still sort of being figured out. One heuristic that I saw someone mention recently is to sort of estimate this way. Ask yourself, what's your maximum block weight? And if you're basing your chain off of like the node template or any of these recipe nodes, then your maximum block weight is 1 million. And ask yourself, okay, how many of these transactions should fit into a block? Let's just say like 1,000. So max weight equals 1 million. And let's say like num of these transactions equals 1,000. So if we have this much weight available and we want this many of them to fit in, then we know that the weight per transaction is, we just divide those, and that's going to come out to be 1,000. So maybe I'll just update that. So that's like that's essentially what we're trying to quantify with these weights. Okay. So here's a different one. Here's a more complex one where you can see I'm passing in some number n, and then inside the call, I'm going through some loop n times. So if I'm going through this loop a number of times proportional to a value that the user passed in, that means I need to charge them a value or a weight proportional to whatever they passed in. So here I say linear 200. And what that means is it's going to be 200 times whatever this n is. So I'll show you that. So here's the struct linear, you know, it has some value. That was the 200 I put below. And then we implement way data. And so again, here's the tuple. We only had one parameter that time. So the tuple is only one element long. It takes a reference to a U32. And all we're doing is, you know, like I said, we're multiplying the parameter times this 200 that was coded in here. So X saturating multiply by 0. Or not, I mean, not the number 0, this like that 0th element. Yeah, so there's a lot more to dig into here, and I think I don't want to spend too much time on this recipe. So let me just look back at the troll box. Yeah, nice. Okay, why event params args cannot have names? Transfer account ID. Yeah, great question. I wish they could. So let me sort of point out what the question is. Okay, here, let's go back to the appetizer one that we were looking at called, what was that called? So we had this appetizer about events. Oh yeah, events verify execution, and it was, oh yeah, right, simple event. So where is that? Here we go, simple event. So we had this decal event macro here, and there's like a couple of them, you know, like, I don't know, whatever. There could be some dot comment here, and then there could be like, here, I'll make this clear, some event, and then there could be like other event, and maybe I'll call it like, well, we're just being silly right now, and it might have like 2 different things in there. And so the question was, you know, that makes sense, but sometimes these things get super long, you know, like maybe there's 3 values in there, maybe there's 3 values and also like an account ID or something. And eventually when these things start getting long enough, it's hard to remember what each one of these was. And so if I understood the question correctly, it was like, why can't we do something like this, where we name these things and the value is like X with type U32 and Y with type U32, and, you know, use this kind of tuple. And my answer is, I don't know, that seems like a good idea. And actually, to be honest, I don't know that you can't. I'm not sure I've ever tried it, but it seems like it would be nice. So, well, maybe let's just, I mean, I don't know, let's try to compile that thing. What is this one? Simple event, cargo check -p, simple event. No rules expected this token. Okay, well, that pretty much answers it. Like, that's telling us that the reason we can't do this is because our decal event macro wasn't expecting that kind of a variant. Now, I don't know if that's for like some fundamental reason or just because we haven't gotten around to making it do that yet. So yeah, that would be something worth looking into. Yeah, and another thing I'll say here is, like, you know, you guys actually just watched me learn something that I didn't know before. So it sort of emphasizes the point that the best way to use the recipes, reading them is great for sure, no question, but hacking on them and playing with them is even a way to learn more. Next question, would it make sense to compute the weight, or is it more to give it kind of soft priority for balancing execution order? No, it's not about priority. So it's about, I mean, so, okay, you, in the default implementation of the transaction queue, so the transaction queue is where priority is handled. So like, let me go all the way back to, where is that? This diagram. So far we've been looking at the runtime. There's this thing called the transaction pool. And so when I, as a user, go to submit a transaction, I send it in through the JSON RPC, it goes into the transaction pool, and then it waits for consensus. Well, it gets validated a little bit. If it's obviously wrong, it gets thrown away. And then we wait for consensus to come along and say, hey, transaction pool, tell me about all the transactions in order of priority so that I can author a block. Now, if you use the standard Substrate transaction pool, it's not going to be prioritizing transactions based on weights. If you want your transactions prioritized based on weights, you totally can do that, and it probably wouldn't be that much of a hack. You would just end up taking the code from Substrate's transaction pool, copying it, modifying it the way you like, and using it instead. But transaction pool has a separate notion of priority that can be arbitrary and can be interpreted by your runtime, you know, any way that it sees fit. So like in Bitcoin, the way that you prioritize your transactions is whichever ones have the most fees for the miner, those are the highest priority. And in Substrate, there's actually this example called the UTXO workshop that is a Bitcoin-like chain, and it does exactly that. So if you want your transaction pool to prioritize transactions that way, that sounds like a cool idea and something totally hackable. And I would be happy to take a recipe for that, actually. Wouldn't it make sense? Wouldn't it make sense to compute the weight? Yeah. Okay, cool. So another thing, since we were on weights for a second, just something that I had forgotten to mention is that when you're computing the weight, so I almost fell into this example when I was writing the recipe. The whole reason we're computing weights is to be sure that we don't have too much compute happening on chain that people aren't paying for. And so when you're computing weights, you want to make sure that the function that does the computing of the weight is itself not very computationally expensive. So like, let me show you one. Oh, I already switched to a new spot, but that's okay. We can come back. So yeah, this linear one is super simple. It's just a single multiplication. There was one up here that used an if. That one was called, or even the quadratic one is just a couple of multiplications. And conditional was just a single if. If you ever find yourself trying to do something inside of the weight calculation, that, like for this in like whatever, and then inside of that loop, have for that in another thing, like that's a sign that you're starting to have too much computation in the way data thing. This is too heavy. And you don't want to spend as much computational power computing the weight as you would have to just run the transaction in the first place. So, okay, I want to just show you guys some things that are close to my heart because they're recipes that I've written recently. So when I inherited this project a couple months ago from my colleague and friend Amar, most of the recipes were about pallets that go in the runtime. And they still are. Most of them are still about that. But I've started to add a few more, and I've started to branch out. Like we actually saw there are a few about runtimes. Oh, and in fact, I should point this one out. So we looked at weights for resource allocation. There's another one called transaction fees for economic security. And this recipe, which I'll let you guys read, is all about how you take that notion of weight that we just described and turn it into a concrete number of tokens that need to be paid. Because there's still some more questions to be answered, like, do you want those weights? Are those just literally the number of tokens you want to pay? Or do you want to multiply it by some scale factor? Or, maybe there's a quadratic response there. And then the next question is like, okay, what token are we paying this in? If your chain only has one token, that's a pretty straightforward question. But some chains have multiple tokens. And so you have to answer the question of like, which asset are we paying the fees in? So some recipes like this one are not about pallets, they're about whole runtimes. And one that I'm really proud of that I worked pretty hard on like a week ago is called proof of work, or called what the heck did I call that? Basic proof of work. There we go. And so this recipe is actually about an entire node. And so what this one does, if we look back at our diagram here, instead of focusing on just a single pallet in the runtime or focusing on the runtime as a whole, this one actually is the first recipe that focuses on another part, the consensus. And there's no reason there can't be more recipes in the outer node, like we just brainstormed one about transaction pool, or there could be a good one, fork choice rule. I think right now we use longest chain, and I think there's also one for the ghost rule, but there's 1,000 interesting fork choice rules that would be fun to code up. And so if anybody's inspired for any of that stuff, I'd happily take PRs to the recipes for that. So let's see. I could have just shown the diagram here because this one's the same consensus-like thing. So yeah, I mean, I guess we've got like 5 minutes left, so let's just start to dig into that proof of work one. So so it won't be in pallets this time, and it won't even be in runtimes, but it would be in nodes. And here's the basic POW node, or the basic proof of work node. And there's a couple files in here, and when you're working in the outer node, the place where most of the interesting stuff happens is this file called service.rs. And one thing that you'll notice is with every one of those pallet examples that we looked at, we always started with this line where we told it to use no STD environment. But when you're working in the outer node, that stuff compiles to standard environment. So you get to use it all. So like whatever your favorite Rust dependencies are, you can totally use them. Like look at this, we're using atomic reference counting from the standard library, and you can totally do that. I guess like maybe just to start showing a little bit about this one, we have this file called pow.rs or proofofwork.rs, where we actually implement a proof of work algorithm. There's this trait it comes with Substrate called POW algorithm. And, just like everything else in the recipes, when you encounter that, there's a link that takes you to the Rust docs, and it tells you, here's the required methods. If you think you're going to write a POW algorithm, you need to come up with a way to determine the difficulty. You need to give me a function that helps me verify blocks. And that means like, if you get a block across the network from some other miner, you want to make sure it's valid before you put it in your blockchain and start mining on top of it. That's what verify does. And then you need a function called mine, and that just does exactly what it says. That's what mines new blocks. So down here at the bottom of this pow.rs file, there's some like type parameter stuff going on here, but essentially we implement the POW algorithm trait for this particular struct I created called SHA-3 algorithm. And there's one associated type. We're just saying we're using 256-bit integers as our difficulty. And then we give it those three functions. Difficulty, this is as you noticed from the title, this is a basic POW. So the difficulty is pretty easy. We just use 1 million every time. It's fixed. Not great for real world, because what that means is like, oh yeah, it even says it right here. Like as you get more people mining on the chain, the blocks will get faster and faster. So in an upcoming recipe about a more realistic proof of work, we'll show like a proper difficulty adjustment algorithm. And then I, implemented those other two functions. So there's verify and there's mine. So yeah, I think I'm gonna try to turn my camera back on and then close the video. Okay, cool. There we go. So, we've got more questions. Hooray. Let's see what we've got here. Oh, it's the same three questions. Yeah, that was silly. Okay. So guys, I'm gonna just end it there. I think that's about 2 hours. And I want to thank you guys all for like your attention and for the good questions and everything. And I'd really love to see you around the recipes in whatever capacity feels appropriate to you, If that's just as a learner and someone who comes to me and says like, yo, I'm stuck on your recipe, I didn't get it. That's awesome. If it's as someone who knows a little bit of Substrate and wants to contribute a recipe, that's awesome too. And, it's easy to transition between those two. Maybe you start out as a question asker, and then at some point you fix a typo, and at some point you fix some code, and, from there it just keeps going. So, yeah, looking forward to it. I guess I do want to show just this last like closing out slide. Oh yeah, that one's probably half screen because my video's on, but it says like, more places to get started. The hub of it all is substrate.dev. That's our Substrate developers hub. So let me just take you around this. Whoops. Substrate.dev. Great. Here's the recipes. That's what we talked about today. There's also tutorials. I've written some of these and my colleagues have written others. And especially these first four are really useful and good places to get started. These other ones are good too. They're a little bit less maintained, but it's always clear what version they work on. This is actually the UTXO1 that is a Bitcoin-like runtime that I was talking about. And then there's also the docs. This is like conceptual docs. If you want to maybe not be so close to code, but understand some stuff about like the Substrate runtime. Here's a great figure that's a lot like the one I showed, and it tells you all kinds of stuff. Here's the one about transaction weights, which we also talked about today. And then the last one I want to tell you guys about that's not up in the title bar here, but is linked from the footer. I thought, yeah, Substrate seminar. So every Tuesday, and that includes tomorrow at 1400 UTC, I do this online collaborative learning group, and it's in some ways similar to what we did today. You know, we'll dive into code, we'll talk about Substrate. The difference is it won't be all me. It could be you presenting what you're working on, or someone saying, hey, here's a cool thing I was hacking on, but then I got stuck and now I need help. So yeah. Okay, cool. Look forward to seeing you guys all next time or at seminar. Thanks a lot.